Hello, everyone. Welcome to my presentation. This presentation is for my final year dissertation project. My project topic is stream topography survey by UAV. UAV is the abbreviation for unmanned aerial vehicle, which is now widely used in forestry sector. One of the classic applications is measuring quarry stockpile volume through photogrammetry structure from motion modeling. To measure stream bed, the current problem is it's hard to get accurate results due to the distortion of water. The objective of my project is to find a method that can get the result with a level of accuracy suitable for stream crossing designs. So why do we need measure the stream topography? The NESPF requires all crossings to provide fish passage. And by having the stream channel shape can help us to effectively design our crossing structures to provide suitable hydraulic for the fish. So how accurate do we need for the measurement? Here are some survey standards I found for crossings, drainage, and roads. The last one is for NZ State Highway, which requires 50 millimeter horizontal and vertical accuracy. For forestry crossings, we don't need to be that accurate, so it's reasonable to set the goal to 100 millimeters horizontal and vertically. There are some advantages for UAV survey over traditional terrestrial surveys. The traditional method is to measure a few points along a cross-sectional direction, while the UAV can collect high-resolution terrain information of the entire study area. And UAV survey can be done by one person and not require physical contact with the stream bed. The other remote sensing method, such as echo sounder or barometric green lidar, can get super accuracy result, but not many forestry companies have this sort of equipment. The data is collected from a stream in Christchurch. Two sets of drone imagery were collected and processed to get the point cloud and digital elevation models. The ground control, the control data was 121 point data collected by a survey grade GPS unit with the antenna. This graph explains how the depth of water is corrected. The camera detects position of the object by the light reflected from the object. This is a point underwater, and this is the water surface. The camera will think the object is here due to the refraction of the water. So our goal is to find out the accurate depths from the apparent depths. This can be achieved by multiply the apparent depths by a correction factor. Two methods were tested. One is to apply a constant correction factors as the camera angle is quite small. The other one is to apply a specific correction factor for each point in the point cloud. This graph shows the error distribution of each model. The differences between the elevation of the control point and the elevation of the point cloud is the error. As we can see, by applying the correction method, the mean of error is very close to zero. And for the uncorrected method, the mean of error is about negative 0.1 meters. This graph shows the error against water depths. For uncorrected model, there is a significant correlation between error and water depths. By applying the correction method, the systematic error caused by water is eliminated. This graph shows the elevation from the point cloud versus the elevation from of the control points. As we can see, for models not using the ground control points, there's a great difference of the elevation between control data and measurement data. But in stream crossing designs, we don't need the elevation to be accurate, since what we care about is just the stream of the channel. This screenshot shows the cross-sectional profile before and after using the correction. From the result, I found that both correction methods can improve the performance of estimating water depths, and by flying the drone at a lower altitude and using ground control points can improve the accuracy. From my study, I found that refraction correction is essential for getting accurate stream channel. The optimum flight altitude for capturing the drone image is about 30 meters above the ground. The multi-angle method is a bit more complex to use, but has a better result than using a single constant correction factors over the entire stream. Using ground control points can improve the accuracy of your drone model, but it takes time and high accuracy GPS equipment to measure the coordinates of the GCPs. A better solution is to use an RTK drones. Lastly, the 100 millimeters accuracy is achievable using UAV structure from motion survey, but the data collection and processing need to be performed appropriately. Thank you.